Need to test your MCP server, but don't want to deal with network calls or separate processes? We'll show you how to create a FastMCP client that can connect to 3 different server types with the same simple interface: an in-memory server for testing, a remote HTTP server, and even a local Python script. You'll see how to list available operations and execute tools with just a few lines of code, all while handling the connection lifecycle properly.
Import Asyncio. From FastMCP import client, FastMCP. Hash in-memory server, ideal for testing. Server equals FastMCP, test server. Client equals client, server. Hash HTTP server. Client equals client, https://example, com/mcp. Hash local Python script. Client equals client, my MCP server, Pi. Async def main. Async with client. Hash basic server interaction. Await client ping. Hash list available operations. Tools equals await client list tools. Resources equals await client list resources. Prompts equals await client list prompts. Hash execute operations. Result equals await client, call tool, example tool, param, value. Print result. Asyncio, run main.
This demonstrates the client proxy pattern for protocol abstraction, where a single interface handles multiple transport mechanisms and server types. The FastMCP client acts as a universal adapter, letting you interact with in-memory servers, HTTP endpoints, or local scripts through identical method calls. What makes this distinctive is its transport inference system, which automatically selects the appropriate connection strategy based on the input source. The pattern works by cleanly separating protocol operations from transport details. The client manages all MCP protocol interactions, like tool execution and resource access, while dynamically delegating connection handling to specialized transports. This separation enables consistent behavior whether you're testing locally, connecting to a remote API, or integrating with a subprocess, all without changing your application code. This approach solves the problem of transport-specific boilerplate in distributed systems. You avoid writing separate connection logic for each server type, reducing complexity in testing, deployment, and multi-server scenarios. The trade-off is a slight abstraction overhead, but the benefit is maintainable code that works uniformly across development, staging, and production environments. It's particularly valuable when building systems that may need to switch transports or interact with multiple server types. Let's break it down.
Import Asyncio. From FastMCP import client, FastMCP.
Imports Asyncio for asynchronous I/O operations and the client class for connecting to MCP servers. The FastMCP class enables creating in-memory servers for testing, ensuring consistent behavior between development and production environments.
Hash in-memory server, ideal for testing. Server equals FastMCP, test server. Client equals client, server.
This instantiates an in-memory FastMCP server for testing, eliminating network dependencies. The client connects directly to this ephemeral instance, enabling isolated unit tests without external services. This is the standard pattern for testing FastMCP interactions locally.
Hash HTTP server. Client equals client, https://example, com/mcp.
This initializes a FastMCP client targeting a remote HTTP server. The URL points to the MCP endpoint, enabling interaction with a hosted FastMCP instance instead of a local server. Use this pattern when connecting to production or shared MCP services.
Hash local Python script. Client equals client, my MCP server, Pi.
This instantiates a FastMCP client that connects directly to a local Python script acting as the server. The script, my MCP server, Pi, must implement the FastMCP server protocol, enabling local development and testing without network overhead. This pattern mirrors how you'd connect to a remote server, but with zero deployment friction.
Async def main. Async with client. Hash basic server interaction. Await client ping.
This defines the async entry point using Python's context manager pattern. The async with block ensures the client connection is properly initialized and cleaned up, preventing resource leaks. The ping call verifies server connectivity before proceeding with operations.
Tools equals await client list tools. Resources equals await client list resources.
These calls discover available server capabilities. List tools enumerates all executable functions, while list resources identifies available data assets or references, critical for dynamic tool selection at runtime, eliminating hard-coded dependencies.
Hash execute operations. Result equals await client, call tool, example tool, param, value, print result.
This executes an AI callable tool remotely. The call tool method sends the tool name and parameters as a dictionary, returning the processed result. This is how FastMCP bridges Python logic to AI workflows. The pattern mirrors standard RPC. Name the function, pass structured arguments, handle the response.
Asyncio, run main.
This boots the async event loop and executes the main coroutine. Required for running async code at the top level, it handles the event loop lifecycle automatically. Without this, the async functions would never execute. FastMCP client architecture. The transport inference system automatically selects the optimal connection method based on input type, while the client handles all MCP protocol operations through a unified interface. The in-memory transport is the only option that doesn't require network I/O, making it uniquely suited for testing, but completely unsuitable for production. This separation of concerns lets you write code that works identically across HTTP, SDDO, and in-memory connections.
The transport that disappears becomes the only transport you see.